Okay, locate, this is example 5. Welcome back. We're in section 4.3. We want to find the critical points of the given functions, find the open intervals on which the functions increasing and decreasing, identify and classify all extreme values. So it's a lot of stuff. However, this first one involves the extreme value theorem. Now, I won't always tell you that, but early on probably I will. But how do I know? Well, f is a polynomial. F is continuous on this closed interval. So we are guaranteed an absolute max and absolute min. Well, first let's find the critical points. I call them CPs. How do we find them? Find where the derivative is equal to 0. Okay, or the derivative does not exist. I almost forgot to say that because in my head I know that this is a polynomial and its derivative exists everywhere. But what is the derivative? Negative 2x. Whoops. Let's try that again. Negative 2x. So when does that equal 0? Well, set it equal to 0. So f prime of x equals 0 when x equals 0. So there's only one critical point. So what are we going to do? We're going to, and we also have to find where it's increasing and decreasing. So to do that, we set up test intervals. And we're going to check the sign of the derivative either side of the critical point. So here we go. Critical point is at 0. So create a number line. And in this case in particular, remind yourself that we have a closed domain. So we want to test the sign of the derivative either side of 0. So you pick a number, test negative 1 over here, and maybe test 1/2 over here. Don't test an endpoint, test an interior point. So here's my derivative. If I plug in negative 1, this will be positive, won't it? So my function is increasing in that interval. F prime is positive, your function is increasing. When you plug in 1/2, the derivative is negative, so your function is decreasing in that interval. So if I wanted to answer that question, I would say increasing on negative 3 to 0, decreasing on 0 to 1. And we're talking about F. So maybe I'll say F is doing this. Now, the nice thing about this test intervals is that it gives you a good visual. Doesn't that just look like a maximum? Because your function is going up and then it has a horizontal tangent, then it's going down. And yes, that is the case. Okay, so we found the critical point. We found the intervals when it's increasing and decreasing. And now we need to classify the extreme values. And we're guaranteed an absolute min and an absolute max. So what are we going to do? We're going to check the endpoints and we're going to check the critical point. So what do I mean by check? Evaluate the original function at the critical points and endpoints. The highest value will be our absolute max. The lowest value will be our absolute min. So the critical point, x equals 0. What is f of 0? 4. When x equals negative 3, that's an endpoint. F of negative 3 equals 4 minus 9, which is negative 5. And when x equals 1, well, f of 1 is 4 minus 1 equals 3. So here is my absolute maximum. Here is my absolute minimum. And remember what our test interval looked like. We had increasing towards 0, and we had decreasing after 0. So you're looking at a parabola that opens downwards. The critical point at 0, this was the vertex. The vertex occurs at 0 and it has a y value of 4. And then the absolute minimum was over here at negative 3 and was equal to negative 5. We can draw this graph. Let's try that. Let's see what this graph should look like. This is a parabola that's turned upside down and has a vertical shift 4 units up. Now, I know that it looks something like this. It goes through the point, the zeros at x equals 2 and negative 2. Now we have a domain of negative 3 to positive 1. So that point down there at negative 3, let me draw this a little further. This was where we're going to cut this graph off with a solid dot at negative 3, negative 5. Here is our maximum of 0 and 4. The other endpoint was here, so we need to cut this piece of the graph off. And this was the point 1, 3. So that's what my graph looks like, and that's why this is the absolute max. This is the absolute min. But notice we did not need to graph this to find this information out. We just used our theorem that tells us the only places we're going to have extreme values are at endpoints and critical points. Very valuable tools. All right, here's our second example. So let's first of all find our derivative. Negative 3x squared plus 4x. It's worth double checking that I didn't make a mistake there because everything that follows would be wrong. What is the domain of h? All real numbers. So why did I check that? There are no endpoints to worry about. Okay, so we're going to find where it's increasing and decreasing. The first thing we want to do is find the critical points though. So set your derivative equal to 0. So what does that look like? Negative 3x squared plus 4x equals 0. If it was me, I would factor out negative x, leaves me with 3x minus 4 equals 0. My critical points happen at x equals 0 and x equal 4/3. How did I get that? You set each factor equal to 0 and solve for x. Okay, so now we need test intervals. We want to find where is it increasing and decreasing, and do we have actually a max or a min at these critical points? This function is a cubic, and it's possible it doesn't have a max or a min. So how do we set up the test intervals? Draw a number line. We have to check at 0 and at 4/3. That's a little bit bigger than 1, right? So let's keep that in mind. The number 1 is somewhere here. Probably that's what I'll test. And negative 1 would be another good number to test. And what are we trying to find? In here, we're interested in the sign, positive or negative, of the derivative. And our derivative is best looked at in factored form. Okay, so we have 3 test intervals, 1, 2, 3. In this first interval, I'm going to check x equals negative 1. I have 2 factors in my derivative. When I put negative 1 into that first factor, it becomes positive. What about this second factor? If you plug in negative 1 there, is the overall expression positive or negative? I claim it's negative. So my derivative is negative, and my function is decreasing in that interval. Okay, let's test positive 1 the same way. First, you put it in the first factor here. Test positive, put positive 1 in for negative x, that would become negative 1. If you put positive 1 in here, I have 3 minus 4, that's also negative. What happens when you multiply 2 negatives together? You get a positive. So in this interval, my original function is increasing. Now, out here, let's test 2, perhaps. And again, plug it into that first factor, that would be negative. Plug it into the second factor, that would be 6 minus 4, that's positive. So overall, I am negative there, and my function is decreasing in this third interval. Now we're going to write this down on the next page. Okay, so we would say G is decreasing on these intervals, negative infinity all the way up to 0, and 4/3 to positive infinity. These are the open intervals where G is decreasing and increasing on that middle interval, which is 0 to 4/3. Now, we also can tell from our test interval that I meant to get us another page. Forget this guy. Let me write down what our function is. Sorry. So we need to copy this down on another page. I'm going to try to duplicate this page and write down the relevant information. Okay, so we need to write down the intervals on which H is increasing and decreasing. So I would say it like this. H is decreasing on negative infinity to 0. That's this open interval here. And 4/3 to positive infinity. That's this open interval here. That's where we know the function is decreasing, and it's increasing in between. That's this open interval in here. Okay, now we need to classify any extreme values. And this is what's nice about our test intervals. I can see that there's going to be a local minimum here. Just because it's going down, if it has a horizontal tangent, and then it's going up. And here is a local maximum. And I know that there's no absolute extreme values. Oops. How do I know that? Well, that's because I know what the end behavior of this function is. This is a polynomial that goes up on the right and down on up on the left and down on the right. So it can't have it. It's third degree. Any odd degree polynomial cannot have an absolute extreme values. So now we just have to figure out what they are. So H has a local maximum of blank at x equal 4/3 and a local minimum of blank at x equal 0. So the local minimum is easy to figure out. H of 0 is 0. Remember, these are y values that come from the original function. So what about H of 4/3? Well, I guess we're just going to have to crunch the numbers. That'd be negative 4/3 cubed plus 2 times 4/3 squared. And you can pause and do that, and I'm going to do the same. Okay, if you did this, you should have gotten 32 over 27. And you can always, when you're doing your homework, you can graph it. Make Desmos do the most of the work for you. But you should find these places before you graph it, afterwards. So graph it afterwards and confirm that you're looking at the right thing. It's very rewarding to do that. All right, so each of these problems involves quite a lot of work, but you'll. This was just such good practice. Now, let's see if we can get this one done in the remaining 10 minutes that I have. So what do we need first? We need the domain. So this all real numbers except what? Do you see why? Can't plug 2 into the denominator. Now we want to find the critical points. And remember, critical points must be in the domain of the original function. So we got to use the quotient rule. This, I'm assuming now, is no problem for you. So find this derivative. This would be 2x times x minus 2 minus, what's the derivative of the denominator? That's just 1 times x squared minus 3 all over x minus 2. And now comes the work. And I forgot to square this. So let's do this carefully. I multiply out the numerator. I have 2x squared minus 4x minus x squared plus 3. And everybody look at that and make sure you agree with me before we go on. 2 times x, 2x times 2. This minus sign gets distributed. So what does this look like? It looks like x squared minus 4x plus 3. Now, this will equal 0 when the numerator equals 0 and the denominator does not. So we want to see if we can factor the numerator. That would make our life easier. If it does factor, it would be like this, wouldn't it? Now, does that make sense? I think that looks good. So obviously we need a new page, so hang on. Okay, remember what we're doing. We're trying to find the critical points. So these will occur when x equals 1 and when x equals 3. And keep in mind, um, g of 2 is not defined, and neither is the derivative there. So this is not, even though g prime of 2 does not exist, x equals 2 is not in the domain of g. So that's why it's not a critical point. Okay, what happens at x equals 2? That is not a yeah, it is. It's a vertical asymptote. X equals 2. Okay, so there's my critical points. Now we set up test intervals. And to determine where it's increasing and where it's decreasing, sometimes I'll do something to remind myself that this is a vertical asymptote, that I don't want to use 2 as a test point because that's not in the function. And so I need to check the signs of my derivative in actually 1, 2, 3, 4 intervals, because we have to check either side of a vertical asymptote to see what happens to the original function. So g, here is our derivative. It has 3 factors that we're going to be dealing with. So pick a number over here. 0 is easy to handle. I plug 0 into this first factor, that's negative. Into the second factor, that's negative. Into this down in the denominator, well, guess what? Our denominator is always positive, isn't it? Because it is squared. This one is always positive. So over here, what can I say about the sign of my derivative? Negative times negative is positive. So I am increasing as I approach 1. Okay, now pick a number between 1 and 2, like 1 1/2, 3/2. Do the same process. Don't have to worry about the denominator. 3/2 minus 1 is positive, but 3/2 minus 3 is negative. Again, I'm just plugging them in to these factors. So overall, my derivative is negative here, and I am decreasing. So this is going to be a maximum. Now, pick a number in this third test interval, like maybe 2.5. Sometimes decimals are easier to work with. We know the denominator is going to be positive. The first factor of the numerator is positive. The second factor, though, is negative, because 2.5 minus 3 is negative. So overall, my derivative is negative in here, and I am still decreasing. One more interval. Let's just plug in 4. Positive everywhere. Okay, so let's see if I can get this written down. What do we know about G in terms of increasing and decreasing? G is increasing from negative infinity to positive 1 and 3 to infinity, and decreasing from 1 to 2 and 2 to 3. Okay, we're going to run out of time, so you have a local max at x equals 1 and a local min at x equals 3. Figure out what they are and then come back for the next part of this lecture.